Okay. Hi everyone, my name's Leonardo. I'm from Team 52, a Sapienza rocket team from Rome, Italy. I'm the project manager of this year's competition project that is called Medusa. She's Sofia, and she's the head of our structures department. We will be presenting an overview on design, analysis and manufacturing of composite sandwich fins that are intended to be mounted inside of a modular fin canister architecture. So here you can see a photo of our fin canister. The main requirements for the design were the ability to assemble and disassemble it for easy transport, and that is because being an international team, we need to fly in with our rockets, so it must come down to the smallest pieces possible. And also the ability to substitute a single fin in case it gets damaged during the test flight. And this is a little bit of a foreshadowing for later. We'll see what happened with the test flight. One other main concern was being as lightweight as possible while maintaining an adequate safety margin on the aeroelastic flutter stability. Okay. So in order to attach each fin to the 4 aluminum rings of our fin canister, we decided to integrate an aluminum insert inside of the fin structure. It is integrated during the layup process. And there's the need for this aluminum piece is to efficiently transfer the loads from the fin to the fin canister and then to the entire rocket assembly. Okay, here you can see a section of our fins. There's the aluminum here in gray, then there's the carbon fiber, and the yellow is the core material. So we have a adhesive film that is put at the carbon to aluminum interface to improve bonding. And then we have decided to put a protruding bulb geometry on the aluminum insert. This, together with the reinforcement in the middle and the active core material, provides a mechanical interlock that assures the integrity of the entire structure. The carbon fiber reinforcement on the inside also contribute to the overall stiffness of the fin, but the main action for stiffness comes from the outer skins. The core inside is called Koridium, and it is produced by our partner company that helped us with the manufacturing of the fins.
So, in order to find the best configuration in terms of aeroelastic stability, we decided to perform a series of finite element analysis, both on an airfoil configuration and a flat plate configuration. And through the Nastran solvers 103 and 145, we were able to assess model characterization, so how the fin behaves in terms of model shapes, and fin flutter velocity, as well as the optimal number of plies per skin. So let's start by talking about how Nastran, which is the software we used, performs the analysis. So first of all, the model consists in a superposition of 2 meshes, an aerodynamic one and a structural one. And basically, the solver 145 takes the 2 meshes and couples them through linear interpolations of nodes. And the aerodynamic model is that Nastran used is based on the doublet lattice method, which basically takes the aerodynamic lifting surface and discretizes it in panels through the chord and the span of the fin. As for the structural model, the structural model comprises geometry, material, and boundary conditions definition, and I'll talk a little bit more about it later. So the first aeroelastic analysis we computed was done on a flat plate configuration, 4 millimeter thick full carbon plate configuration, which had the same plan form of the airfoil one. And the simulation was conducted on a Mach range between 0.1 and 6 at sea level Earth density, and considering only the first four model shapes of the fin. And as you can see from the root locus diagram, which is this graph here, so basically this graph plots the evolution of the first four model shapes with respect to velocity. Hence, each point corresponds to a different airflow velocity. And on the axis, there is the real and imaginary part of the eigenvalues of the system. And as you can see, the flutter velocity ended up being at Mach 1.5. And on the plot, it corresponds to the point where one of the first of the four model shapes crosses the imaginary axis. As for the airfoil fin, this is a little bit of a characterization of the structural mesh. So basically, the airfoil was modeled as a coreless carbon fiber shell with a 2D discretization. This was done in order to avoid any unnecessary complications in terms of modeling. Hence, the core material doesn't really significantly affect the internal structural stiffness of the fin, as well as the aeroelastic behavior. And as for material modeling, we decided to model it as a two-ply laminated composite skin, which ended up being the best configuration in terms of optimal number of plies. And the fin was eventually clamped at the root interface. This was done because this was the most realistic boundary condition. So here you can see the same graph as before, but for the airfoil configuration. So the root locus diagram actually shows that none of the four model shapes crosses the imaginary axis in the given Mach range. This means that fin flutter velocity occurs above Mach 6. And it's clear, and we can safely say that the airfoil configuration was the best and most resilient to flutter instability than the flat configuration. In the end, we eventually decided to compute a final aeroelastic stability analysis, and this was done based on data resulting from our mission analysis department simulation on a nominal flight. And as you can see, the system remained stable throughout the whole flight and with a good safety margin.
Okay, now I'm going to talk a little bit about the manufacturing. First of all, I want to add that the design was entirely carried out by ourselves with a little bit of help from our partner company that gave some tips about the manufacturing processes, since they specialized in that other than the production of the active core material. The company is called Alia Mentis, and the product is called Koridium. Can you get the next slide, please? In here, I'm going to show some photos of our members at work at the partner facilities, because they provided the molds and the materials and a little bit of expertise, but then most of the manufacturing was carried out by our members. On the left, you can see the right skin, being laminated on the right half of the mold. And then the same thing was carried out for the left half. They are not entirely similar, because the right half has a seam allowance on the leading edge and the tip of the fin, and this will be used later. On the right, you can see the adhesive film being applied on the surfaces where the carbon fiber plies touch the aluminum insert. Going on. On the left, you can see the right core half being aligned with the help of the aluminum insert inside of the third part of the mold. After it is aligned, the insert is removed so that we can place the internal reinforcement where the bulb of the insert is. Then the insert is inserted again, and a single ply of carbon fiber is laminated right in the middle of the fin. After that, so we are at this stage. After that, another ply of carbon fiber is inserted to do the left part of the internal reinforcement, and then the left half of the Koridium core is placed. Now we can fold the seam allowance of the right skin over the left core half, and this is done so that when we mate the left skin with the right skin, there's not a tiny contact area, but it is spread over a larger surface. So the mold is then closed with 6 M8 screws, and then it is inserted inside of the press. The press applies a force on the 2 larger surfaces of the mold, and then heats them up to about 280 Fahrenheit. At this temperature, the carbon fiber prepreg starts to cure, and the internal core is activated. Once activated, it becomes a little bit more viscous and applies an even pressure from the inside. So any voids and crevices will be filled by the core, and even if there are some imperfection or tolerancing issues with the mold and the carbon fiber plies, it takes care of that. And the main thing is that it is able to push the inside reinforcement beneath the undercut of the protruding bulb, thus creating the mechanical interlock that we wanted. After 50 minutes, the curing process is completed, and we can open the press and take the mold to a shower so that the temperature can be lowered very fast. The turnaround time of this process is just over 1 hour. And with this, we were able to manufacture 6 fins in just a day and a half of work.
So here are some numbers just to sum up. So in the end, the airfoil configuration ended up having a fin flutter velocity over Mach 6, while the flat plate configuration may experience a flutter instability above Mach 1.5. And the overall mass of the single fin, aluminum insert included, ended up being 158 grams compared to the 201 grams of the flat plate configuration. And as I previously mentioned, the optimal number of plies ended up being 2. And so here we wanted to show you some of the photos of our test flight. We did our test flight about a month ago, and as you can see, it really didn't go nominal. And in fact, we unfortunately had some problems with the re-entry subsystem, so our rocket ended up planting itself to the ground at about 108 feet per second. And in the end, we had to change all 4 fins. One of the main advantages of our design, of our fin canister design and fin design, is the possibility of replacing each fin individually. Unfortunately, we weren't that lucky. And nonetheless, we were very satisfied with the result. In fact, if it was only for the structural adhesive, the composite fin would have completely detached from the aluminum insert, as it actually did where the bulb geometry wasn't present.
So if you want, we can pass around some samples.
Yeah, we got a section fin, so where you can see the internal structure. And the core material, unfortunately, they didn't cut it where the bulb is, so you can't really see it. But yeah, you can feel how light they are. So I don't know if you want to.
There's also the damaged fin. You can see that the carbon fiber detached from the aluminum insert on the back side, where the bulb is not present. But if you stress the two parts, you cannot separate them.
Because they are mechanically interlocked. And so, yeah, you want to thank you for your attention, and we are happy to answer any questions you may have.
I do have a question.
Okay.
Yeah. So, how was the Koridium core material chosen? Did you validate against other materials?
No. The thing is, we had a modular fin canister design from last year that we wanted to replicate in order to not revolutionize the entire rocket architecture. And we were looking for companies that would sponsor the materials to make a sandwich fin. We reached out to Alia Mentis, and they didn't only provide the material, but also their expertise on the processes, and they invited us to their facilities to build the fins. So we had to change our intentions, and we started designing the fin. And after like a month of work, we got some feedback from them, and then the manufacturing process started.
Yeah, so we basically didn't have nothing about... So we weren't actually thinking about composite sandwich materials at first. So we were only trying to find a different solution from last year's, where last year's we used a flat plate configuration 3 millimeters thick, which had like a platform which was a little bit smaller than these years, because we ended up building a bigger rocket in terms of diameter and also in terms of wings, wings platform. And we did want to keep, as Leonardo said, the fin canister design, but we didn't want to make it too much heavy. So we started searching for solutions, and we ended up finding Koridium and Alia Mentis, of course. And yeah, we thought, yeah, cool, let's try that. And also we were able to make our aerodynamic department happy, because it was the first time we were able to implement an airfoil on our actual fin design. So it was, yeah, pretty exciting. Any other questions? Yeah?
Have you guys considered different configuration of fins, like 3 fins, 5 fins? Why is it on?
Okay, so we chose 4 fins for a couple of reasons. The first one is that the same configuration as last year's rocket, but there's a very big reason behind it, and that is because of the symmetry planes. 4 fins, we have less of an effect of the roll position of the rocket with respect to the wind gusts than 3 fins. So I guess in our technical report we put a graph that shows how the static stability margin changes with respect to the direction from which the wind comes. And with 3 fins, we have a pattern that is repeated 3 times, and the difference between the maximum and the minimum of the static stability margin is way higher than with 4 fins. Yeah.
For the aluminum insert, is that something that you machined yourselves or your partner did, or is that something you bought?
No, so the thing is, we don't have any facilities that allow us to CNC machine or laminate with such difficult processes ourselves. So it was entirely carried out by the partner company, obviously with our specifications for the geometry and material.
So the basic design was made entirely by us, but our partner company helped us with some suggestions on the actual design, and also with the manufacturer of the aluminum insert, which was CNC machined, and the entire process, as well as the 2 molds. Yeah, the 2 mold halves were actually designed by them with our geometry specification on the fin.
Yeah, and the thing is, producing the molds is the where the cost is. Once you have the molds, if you build manufacture 4 fins, 8 or 12, it doesn't really add up to the costs. So what we are trying to do with the entire rocket, and also we'll try to do this for the fins, is to reuse most of the components on next year's project that will have an hybrid rocket engine instead of a COTS motor. And the molds are there, so if we need other 4 fins, it's not going to be a real issue to get.
Did you bring any extra fins with you in case of problems?
So the thing is, we originally asked them to produce 8 fins to have a full replacement set, but one of the inserts had a manufacturing issue, and so we decided to do a test run with this, and it ended up being in the fin that was cut in half. For this reason, at the time of the test flight, we had the 4 flight-ready fins and 3 replacements. And then, after the unfortunate event, we readily contacted our partner, and they had already started the manufacturing on the 8th fin. So, I mean, it's what we predicted, what we wanted from the start, and then we were lucky to have them be a reliable partner and enable us to come here and launch, even with this close time between the test flight and the competition. And also, the damage on the 4 fins is about what you see on the fin that we are passing, and they could be. I mean, they are not entirely broken. We could lay some more carbon fiber plies on them and make them usable, but obviously we didn't want to do it for the competition.
Any other questions?
Yep.
Did you do any testing of your fins, like physical testing?
No, so after each fin was manufactured, we did a check with a 3D scanner to verify that it was in the tolerances for all the dimensions.
Non-destructive tests.
Yeah, and then each fin was thoroughly looked at to spot visual imperfections, and then we had the test flight. Yep.
Was the NDT just like on the outside of the film?
I'm sorry?
The non-destructive testing, was it just on the outside of the film? Did it see inside?
Yeah, just the outside.
But actually, the 3D scanner also was able to see if there were any unhomogeneous places inside. So it was most about the quality of the manufactured fin, rather than Young modulus, strength, and so on. But yeah, you were able to see inside through, but only to visually check for any holes in it or voids.
And also the active core is a more reliable process than other types of cores, for the reasons I was telling you about earlier.
Any questions?
Thank you so much.
Thank you for the opportunity.